cell programming part of half of Ginkgo does every day, which is, as we'll talk about, is one half, and then the biosecurity portion is the other half, is one based on one of our 5 founders, a MIT professor named Tom Knight, who came to MIT in the 70s with as an electrical engineer. And his early time at MIT, and making sure I get this data right, but we'll go with it for purposes of this conversation. I think he was like the 5th user of ARPANET, for example, like the 5th node on the network. So like a deep computer scientist, electrical engineer. In the 90s, he kind of said, well, this computer thing is really mature, humorous, obviously, but at that time, if you were the 5th user in the ARPANET, the 90s probably felt very mature. And he said, what's the interesting thing to program going forward? Well, there are these things called cells, and they run on digital code in the form of DNA. Why aren't we programming cells? What is the reason we're not doing it? And he comes to Ginkgo every day, and he'd tell you this story if you're sitting here in first person. It's one of my favorite conversations to have with him. And the short answer was, well, I guess Tom Knight, need to go get an undergraduate degree in biology to really figure this question out. So as a tenured professor at MIT, he goes and essentially gets an MIT undergrad in biology, and then he opens the first wet lab in the computer science department at MIT. And to this day, Tom, I believe, is the owner of syntheticbiology.com. And I'd encourage your listeners to go check it out. So he asked this question, and then his kind of first of many revelations on the topic was, why is this not happening at more scale? Why aren't we programming cells? Well, because it's really hard, right? It's programming a cell. There's so many different types of cells. There's so many different types of genetic programs. We don't really know how they all work. And it's slow and expensive. Why? Because to program a cell, to put DNA into a cell and then grow that cell and figure out what it does for so many years is essentially a manual process done by PhDs with pipettes moving liquids around a lab bench. That is not a scalable process. So what he ultimately kind of focused on was, if we want to do more programming of cells, then you really need to think about the tools, just like early computers. To program a computer early, in early computers, you had to solder together hardware, right? Like in the 90s, you weren't watching computer programmers soldering together hardware. No, so he was like, we have to fix the tool problem, i.e. the problem of making genetic engineering much more efficient. So that's, Ginkgo is an example of this, but Ginkgo's overriding focus for the 13 years or close to 14 years that it's been founded has been to take the lab protocols of a bench scientist, break them down into operational units, and then wrap them in software and put that set of protocols into robotic implementation. And if you do that, then the thing that we measure, there's a bunch of metrics we measure, but the best one to think about is the cost per DNA program written into a cell and characterized. We call that a strain test. Essentially, if you write a DNA program into a cell and then you grow that cell and see what it does and you collect the data. How much does it cost to do that one time?